Hello, what's up everyone? Welcome to this training course where I'm going to show you how to master one of the new, I say new, it's been there for 3 or 4 years, but one of the syntaxes that were added to Swift a few years after its initial release, and one of the syntax that has become very fundamental to, I would say, most of the modern iOS frameworks. And by modern frameworks, I mean frameworks like SwiftUI, like Swift Data. So we're going to be talking about key paths. Key paths are this syntax I want to talk to you about today. Personally, I'm very happy to be doing this training course because in my personal history with iOS development and contributing to the community, actually the first talk I ever gave was about key paths. So it's very nice. There is this feeling of coming back to my roots with this training course. Before I start, I want to give you a small briefing. So if you are watching on YouTube, you have a link in the description to a GitHub repo. If you bought the course on Gumroad, you have in the file that come with the video two playgrounds. So I'm going to show you what you will get either on GitHub or on Gumroad. You can see you have two playgrounds: how to master key paths viewer and how to master key paths and just that. So the only difference between these two is that this one, the viewer one, is the one I'm going to use during the live stream. And basically, I have removed a good part of the code so that we can implement it together. And the second part is the version with everything implemented. So if you want to follow along, I would recommend that you open the viewer playground. This way you can really implement things with me, and by implementing it makes it easier to understand and remember what we're going to talk about. Since we're going to use playgrounds also, we all know that there is a good chance that something is going to crash. So you can also take a bet on the number of time I will have an issue with the playgrounds during this live stream. Finally, two things I still have to say before we start. So if you're watching live, first, thank you for being here, and also remember that you have the chat to ask any question that you have, make any remark that you have. These questions and remarks will be invaluable for people watching the replay. And last thing, if you're watching either live or the replay on YouTube and you enjoyed the content, there is a link to buy the course on Gumroad. So it's the same content. You just have a button to easily download everything, the video and the code, and it's basically a tipping jar. If you have enjoyed the course and you want to leave me a tip, that's possible through this link. If you're watching live, the link is not there yet. I will add it soon. I think that's basically everything I wanted to say. So let's go into the topic and let's get started. So let me rearrange the window so that I don't miss any message in the chat. I see a few people are in the chat. Hey Brandon, hey Protamesh, hello Games Day. Let's get started. So I've opened the playground viewer, and oh, the link on GitHub leads to a 404. Damn it. You know what? Let me just give a look real quick, because of course it sucks if you can't. I'm sure that I've forgotten to make the repo public. Like, that's definitely that. It's not the first time it happens. Thank you for catching it. It's so easy to forget because when I go on GitHub, oh yes, it's private. So I'm gonna fix this right away. Change visibility, change to public. I want to make it public. Okay. I need to get a code by text message. Okay. Okay, now the repo should be public. Okay, now the mistake has been fixed. The repo should be public. Thanks a lot for spotting that mistake. So let's get started. So first question we want to answer is, what's actually a key path? So a key path, if you look at it, it's this syntax right here. So backslash, then the name of a type, and then the name of a property. But most of the time, when you look at a key path, you will actually not see the type being used. It's because key paths are able to rely on type inference. And so if from the context, Swift already knows what will be the type of the key path, then you will be able to use this shorthand syntax where you do backslash dot and then the name of the property. And so if you've seen keepath being used in the context of Swift UI or Swift Data, you've probably seen this syntax. And well, now you know that it's actually an abbreviated syntax, and this is the full syntax. So what's important to know is that a keepath is a generic type that takes two arguments, its root and its value. And we can actually see the two of them in the example. Here, the string is the root of the keepath, and the value is not count, but it's rather the type of count. So here, the type of count is int, and so the value of the keepath is an int. And the root is going to be the type on which the keepath will be invoked, and the value will be the type of the property that the keepath refers to, and so the type of the value that you will get when you invoke the keepath on the root. So let's see actually what a keepath invocation looks like. Let's see what it looks like to just use a keepath. So we have declared a keepath here and a keepath here that works on strings. So in order to invoke it, we need to have a string. So let's create a string. So you can see I'm creating this string that contains the text hello YouTube. And now we can invoke the keepath on the string. So to invoke a keepath, we use this syntax right here. So it's a special subscript that is available on, I would say, almost, I was about to say it's available on every value in Swift. That might not be the case for every value, because functions, for instance, I don't think you can call a keepath on them. Maybe same thing for tuples, but I would say that for nominal types, so types that you can refer to with a name, so an enum, a struct, a class, an actor. Also, you can call keepaths on them, and so you use this special subscript that takes an external name for its argument. So you say subscript, and you pass the argument keepath, and the value is the keepath that you want to invoke. So here we can see I'm invoking the keepath with two different, we could say, syntaxes, two different ways of invoking the keepath. In the first example, you can see I'm passing a keepath with the / syntax, and this is what Swift calls a literal keepath. You might see this term being used, and so a literal keepath is when you create the keepath by using the / syntax. The same way that this right here is a literal string. A literal string is the value that you create by using the double quote special character in Swift. But you can also store a keepath into a variable or a constant like we did here. And then with this variable or constant, you can pass it in order to invoke the keepath. And so you can really think of a keepath as a reference to some property, and we will see a bit later that it's actually exactly what it is. So I see a question, are parameter namespaces important in Swift? So by parameter namespaces, I guess that you refer to this right here, the name of the argument. Am I right? So if that's indeed the case, so this is what Swift calls the external name of the argument, and yes, it's important. This external name is part of the signature of the function. So if there is an external name, you have to pass it when you call the function. Otherwise, you're either making a mistake or calling another function. So this is indeed important. Actually, I'm gonna see if I can do a command click to jump to definition. So it jumped to the definition of the keepath right here, but I would like to do it. No, I can't jump to the definition of the subscript, but let me jump to the definition of the type keepath so that we can see it together, because it's always interesting to see the definition of things. So where have we arrived? I would like to see, so you can see keepath is just a class with keepath, root, and value. And we can see that there is a full hierarchy. I think we'll go back to it a little bit later, but you can see first you have a partial keepath, and it's when you only know the root. You don't know what kind of value it yields. Then from that, Swift builds the keepath, so the keepath where we both know the root and the value, which is a way to read the value of a property. Then we have the writable key path, which is very similar, except that we can also write to it. We will see example of it later. And then we have the reference writable key path, which is basically the same thing, but that allows you to write this time to reference types, so to classes and actors, because writing to a reference type has a different semantics than writing to a value type. Okay. So I said that you can think of key paths as a reference to a property, and right now I've used what we could call a first level property. I was getting the property of something on a value, but of course sometimes you also have nested properties, and key paths also work with nested properties. Key paths can be composed. For instance, if I have a first key path that refers to the property count on a string, and then a second key path that refers to the property byte swapped on an int, and remember that count here is of type int, I can compose the two of them together by appending the second key path to the first key path. And then I could very well invoke this composed key path. So let me do it, and let me show you the result. So this is a weird thing, is because we've taken the byte of we've taken the byte representation of the integer and we've swiped it, so it looks a bit weird. I just wanted to call a property that was specific to integers, and we can see that it works. And so you can compose key path by calling the appending method on the first key path and passing a second key path with a compatible signature. So the second key path, its root must be of the same type than the value of the first key path. Actually, let's go see the signature just to make sure of it. So you can see method appending. So you have a root, a value, and an appended value. And so you pass in a new key path, and you can see that the root of the second key path is the value of the first key path right here. So let me go back to the code, and I wanted to show you that, of course, we can compose key path using this method, but it's useful when our key paths are stored in variables. But most of the time, you will probably just want to do the composition through the literal syntax, meaning that here on the string, if I call the key path subscript, I could say, okay, I want a key path to the count property, and then to the byte swapped property. So you can compose key paths like this through the literal syntax. And this is something that you are much more likely to use than this syntax right here. In general, I would say when you write app level code, you are much more likely to use literal key paths, and code that stores key paths either in arguments or in constants or variables. It's more framework level code that will be using this approach. And finally, every type has a special keyword called \self. And so this can be a bit surprising the first time you see this syntax. Actually, what's interesting to know is that when key paths were first introduced, I think with Swift like 4.0 or 4.1, this special key path wasn't there. It was introduced later because, as it turns out, it's quite important. It actually refers to the value itself. So this key path has its root being equal to its value, and when you call it, you just get the value. So here you call the key path self on the string, you just get the value in the string. So it's called the identity key path. And why is it here? It's because it's actually very useful. For instance, if you have code that composes several key paths together, maybe you need to have an initial value to start your process of appending to the initial value, and this identity key path is a great initial value. From the algebraic point of view, we would say that the identity key path is the neutral element of the operation that allows you to append key path. And so if you've done some algebra, you know that these kind of neutral elements are very important so that you have operations that are well behaved. That's all for this intro to what key paths are. So I've left you a link to the page about key paths on Apple's official documentation if you want to learn more about it. But on this page, we've covered the basics. And so from this first page of the playground, if you need to remember only one thing, please remember that key paths, they are a way to refer to a property. That's really the most important thing. If you have that in mind, I would say you should be able to remember, you should be able to use key paths and not have too much trouble using them. So now let's move on to the second page called Standard Library. So in this page, we're going to see how we can implement some functions from the standard library, like filter, you can see here, and make them work with key paths instead of closures. So if you've used Swift, you're very likely to have used higher order functions from the standard library. And so I mean functions like filter, map, sort, etc. All these functions that operate on a data structure that takes closures as their argument and that allow you to implement, to run algorithms on your data structures quite easily. And we're going to see how we can make these functions work with key paths. We're going to see that key paths are a very convenient syntax when working with this kind of functions. And we're also going to see that through these examples, we'll be able to get a better understanding of key paths by drawing some parallels between key paths and closures. So let's get started with filter. So filter in the standard library is defined at the level of the protocol sequence. So I'm defining an extension on that protocol sequence. And I want to implement an overload of the method filter. But this time, instead of taking as an argument, so a closure that takes an element and returns a Boolean, I'm going to take a key path that has for its root an element of the sequence and that returns a Boolean. And then the function will return an array of elements, just like the filter function does in the standard library. So how can we implement this function filter? So to implement it, we're actually going to leverage the already existing filter function, filter method, the one that works with a closure. So on self, because we are on a sequence, I'm going to call filter, so the version that expects a closure as its argument. So this is included closure. So you can see this interesting symmetry where the root of the key path is the argument of the closure and the value of the key path is the return type of the closure. We'll get back to it later. And so I'm going to implement this closure. So it takes as an element as an argument and needs to return a Boolean. Okay, what's the only way I can return a Boolean from an element? It's by invoking the key path I'm given as an argument on the element. So let's do it. On the element, I'm going to invoke the key path. So I'm passing as an argument the key path I've received here as an argument to the method filter. And that's actually it, unless I've made a mistake, but I don't think so. I've implemented my overload of filter. And so now we can try to use it. So I'm defining an array of integers from 1 all the way through 9. And then I need to have a Boolean property on these integers. So here I want to have the property is even. So I'm implementing it as an extension on the type int. So let's implement this compute property is even. So it's going to be fairly easy. On self, which is an integer we call is multiple of 2. So I wanted to add this example because it's also a great way to show you this nice is multiple function that is in the Swift, that has been in the Swift library for a few years now, and that is not as widely known as it should be. And so now that we have this syntax, we can make line 28 build. So I'm going to run the playground, and as you can see, it works. So I've been able to call my filter method, and so I pass in a closure, and you can see that I get the result that I expect. So I only get in the return array the elements for which the Boolean property that the key path refers to return true. So since the complete property returns true for even integers, I get 2, 4, 6, and 8. And so all the odd numbers, so 1, 3, 5, 7, and 9, have been excluded after I've called the method filter. So that's pretty cool. Now let's move on to map. So by the way, if you're watching the replay, whenever you see me starting to implement something, feel free to pause the video and try to implement it yourself. I won't do the pauses for during the live because it's not great for the people who are watching. But when you are watching the replay, feel free to try and implement it. Usually there is no trick unless I say it, and so the implementation should be pretty straightforward. For instance, here, how can you implement map? The strategy will be the same then to implement filter. So calling the underlying filter and in the closure invoking the key path. So let's do it again. So here on my sequence, I call map, the one that takes a closure. Once again, see this symmetry. The root of the key path is the argument of the closure. The return value of the closure is the value of the key path. And so, just like before, on my element, I'm going to invoke the key path like that. Okay, that looks pretty good. And so now I'm going to call this map function. And as you can see, I get the result I wanted to have. So now instead of the integers as an int, I have the integers turned into strings, as you can see from the double quotes. And so I've been able to call the function map by passing the key path that refers to the property description rather than passing the closure that called the property description. So rather than doing this, so data.map$0.description. The two lines, so line 42 and line 40, yield the same result. They just do it with through a different syntax. Let me remove this line. So that's pretty cool, but with this approach, we need to write a wrapper for each function. And that's definitely not great. It doesn't scale very well. However, notice how I've been showing you this similarity between closures and key paths. And it's all the way to the point that we can basically implement, what we want to implement is a getter. What the function filter or map expect, it's basically a getter, meaning a closure that you can call with a value and it returns a new value that you get from the first value or by transforming the first value. And so this getter, you can implement it through a closure. For instance, here I'm implementing a getter on a string, and so I take the string as the argument, and then either I transform it or I just call a property on the string. But I can also implement the getter through a key path. And what's really important to understand is that these two syntaxes, they are basically two faces of a same coin, because the goal in both instances is exactly the same. We want to get a new value from an existing value. Simply, in one case, we are doing it through a closure, and the other case, we are doing it through this new syntax, which is called a key path. I see a few messages in the chat, so let me take a look. So Pratamashir saying an enum with no cases or computer property or protocol conformances doesn't have key paths. That makes sense. That makes sense because an enum, because then there is like there wouldn't be a way to an enum with no cases. You cannot create an instance of it. So you could, or maybe we need to try, like, do you get a key path for a static property? I would say that yes, but without trying it, I'm never sure like 100% because there could be so many edge cases. But yes, if there is nothing to call, then you won't get a key path for it, because it leads me to this interesting point, which is that key paths are type safe. You can see from the color syntaxing, if I make a typo, so for instance like that, my code won't build anymore. So key paths are type safe. are type safe. They are being generated from our code, from the properties we have defined on our types, and so that's why yes, you won't be able to call a key path on a non-existing property, and that's pretty nice because if you've used Objective-C, you must remember that Objective-C also had this notion of key paths, but it was implemented through strings. And so if you made a mistake when typing the name of a property, or if you renamed a property in code and didn't update the key path in the string, then you would get a crash at runtime. There was also other messages. So will key paths work if a compute variable is asynchronous? Good point. We're going to test that actually at the end of this page because I see a lot of good questions, and it's always best to try them because you never know. You never know. Until you've tried it, it's very easy to try to infer the answer and actually be completely wrong. But first, I want to keep building on this similarity that I was talking about between key paths and closures, the fact that they both implement a getter just using two different syntaxes. And since they both implement the same thing, we could try to turn a key path into a getter function. So we can try to implement a function get that will take a key path as its argument and that will return a function that takes an element of type root and returns a value. By doing this, we would basically be turning this right here into this right there. And as it turns out, it's pretty straightforward to implement. You just need to actually follow the type signature. So this function expects to return a function that takes a value of type root and returns something of type value. So let's just type that. We are returning a function that takes in a value, okay? From that value, from that root, how can we get something of type value? The only way is to call the key path on the root. So let's do it. Let's call the key path on it. And unless I'm mistaken, we've implemented the function. So you can see it was rather straightforward. We just followed what the signature expected us to do. And now you can see if I call it right here, you can see that we can call the function map by passing the key path and turning the key path into a closure through the function get. And so actually I can try and remove, so comment out the code, comment out this code right here. So my overload of map is no longer part of my playground. And you can see that this code still builds. This code here still builds. Why does it build? Because I am turning the key path into a getter closure. Okay. This syntax is nice, but we could make it even shorter because we need to put in the word get, then to add parentheses around the key path, and that's not great. One of the reasons why key paths were introduced is because they are a nicer syntax than a closure. Basically, there are two problems with using closures for getters. The first one is that the syntax can be a bit cumbersome. You need to add curly braces. You need to either use an anonymous argument, so $0, or you need to declare the argument and add the keyword in. So it adds a lot of boilerplate to your code. It makes your code a little bit harder to read. Also, you cannot use the trailing closure syntax in an if statement, for instance. But there is also another problem, is that a key path can contain arbitrary code. So inside this key path that is supposed to be a getter, you could be doing crazy things. You could be doing a network call, for instance. And so this is also a problem. And key paths, they solve this problem because first, they give you a syntax that is nicer to use. You just have this backslash character, but it's a little bit less of a strain on the reader than having additional curly braces, anonymous arguments, or declaration of new arguments. And also, with a key path, you can only have a getter for the property. Your key path cannot do anything unexpected like a closure could do, because a closure at its root is just arbitrary code. And so this get function kind of goes a bit in the way of this philosophy, but we could actually make it even shorter by declaring a custom prefix operator. So we use this character right here, which is called the caret, if I remember it correctly. And so we are going to create this operator so that we can have this syntax work. So we have our key path and we just put this little caret in front of it to turn the key path into a getter function. And the way to implement this operator is extremely straightforward. Once again, if you're watching the replay, try to implement it yourself. But since the signature is the same than the get function, I just need to call the get function. And that's it. I've implemented my custom operator, my overloaded operator, and that makes sense because it's actually just an alias for the function get. And so now this syntax does work. And actually, Swift is even smarter than what I've told you, because the people that were watching and that were particularly attentive to details might have noticed something. It's that every time I was calling the function from the standard library, the coloring was purple. However, if my overload had been called, it should have been green because it would have been user level code, not standard library level code. And there is a reason why the color was purple. It's because Swift is actually able to automatically turn a literal key path into a getter function. So actually, you don't even need to implement this overload of filter. This syntax right here, it works out of the box in Swift. But as with everything, there is a catch, is that when I said that Swift is able to automatically turn a literal key path into a getter function, the important word was literal. So if you pass in a literal key path that you create on the spot inline through the backslash syntax, it works. But now let's say that you store the key path into a variable. So like this. So I'm getting my key path to the isEven property of an int, and I pass it. Now let's see what happens. Now it doesn't work anymore because I'm no longer passing a literal key path. I'm still passing a key path, but a key path that is stored inside a property, a constant, a variable, and that Swift is not able to automatically turn it into a getter function. You can see that Swift lets you know, it says it cannot convert a value of type key path in bool to explicit argument of type function from int to bool. So if we want this code to build, we need to either once again implement the overload of filter. Now let's run it again. So now it works. The only thing that's weird is that the color here is still violet, even though you can see by the highlighting it's this overload that is being used, but it's still violet. I would have expected to turn green actually. So sorry when I said that if you had been particularly observant, you could have noticed something. That was not the case. However, let's see. If I put the literal key path back, okay, it's so weird because it still highlights this one, even though it's not calling this one, because we saw that we can comment it out. So it's interesting to see that Xcode is getting a little bit confused by all of these like overloading. But in this case right here, it's important to understand that this is not the function that is being called. It's just calling the regular filter from the standard library, and Swift is able to automatically transform this literal key path into a getter function. And so that's the reason why these days you don't see this little operator being used anymore. It's because since most of the time, in the vast majority of time when you write app level code, you're just going to pass in a literal key path, and so you can just pass in the literal key path. However, if you were using, if you need to store the key path either in like I was doing. So let me get it. I've removed it. Okay, I'm going to go back to my code right here. So I'm going to create a key path to the property description. So int to description. So this thing is the same thing than this thing. So if I try to do data.map and then the key path, is it going to work? It's not gonna work because I commented out my overload of map that works with key path. Since it's not a literal key path, Swift can't turn it into a getter function. However, we can use the little caret operator to make it work. You can see that it works. I would argue in this case that it's better to use the get function actually, because if you're writing code that takes a key path that is not a literal key path, you're most likely writing a framework level code, and so you might want your code to not rely too much on cryptic things. But what I wanted to show is that in older code bases, you might find this little trick because it was a bit popular when key paths were first introduced, but now they are actually not needed anymore. And what's great is that right now in your code base, if you want, you can start using key paths whenever you are using a closure that just does like $0 dot some property or $0 dot a first property dot a second property. You can use a key path instead. It's gonna work right outside of the box. And what's really interesting in all the example I've showed you is that we've seen that key paths, they are very similar to getters. And so that's the thing that I really want to drive. That's the point I really want to make right now. Actually, if you should remember only one thing from this training course, it should be this, that key paths are a literal syntax to reference the getters and the setters of properties. Once you've understood that, you've understood everything that you need. And so this means that a key path like this that refers to the property count on a string is equivalent to this getter closure that takes a string and on it calls the property count. And it's the same thing for writable key paths and setter closures. And so this also brings us to the question of why do we have this very weird \self key path, which is called the identity key path? It's because I'm sure it has happened quite sometimes that you've passed a closure that just said $0. For instance, let's say that you have an array with nil values, so something like that. So maybe you have 1, 2, 3, nil, then 4, then nil, and then 6. And you want to remove the nil values. What do? You do array with nil values, compact map, and since you don't really want to implement a transform, you just want to return the values and remove the ones that are nil, you do this $0. This closure that just returns its argument. It's something that we use quite a lot in Swift because it's a nice shortcut. And the \self key path is equivalent to this closure. So for instance, if you do array with nil values dot compact map \self, let's see, is this going to work? It doesn't work in that case, and there is a good reason why. It's because so what does it say? It cannot infer, or maybe I need to say like int like that. It's because then it cannot infer. So this is a bit of a bad example because in this case, the closure, since it maps from non-optional to optional types, Swift gets a bit confused. But I mean, I could just do map like that and then map like that right here. Let's see if this one works. I see there is an error. Okay. Cannot infer. Okay. If I say int, I would have expected that one to work. To be honest, that's interesting. That's an interesting one because what's interesting is that the fact that this closure is equivalent to this key path is true when you given how we've seen that key paths work, it's true, but Swift might have a harder time dealing with this key path in this context because I think it seems to confuse Swift a bit. Always a bit frustrating when something doesn't work as you would expect, even though like when you do the reasoning, it should be working. But basically, what you should take away is that this key path is the equivalent of this closure. However, since for Swift, key path and closure are two slightly different things, it seems that in that case, you cannot pass the key path instead of the closure. But at least this should help you better understand why this \self key path exists. And I'm going to remove this code so that the playground is still building correctly. Okay, so that was for the second part of the second page of the playground. Before we do, we wanted to test a few things. So for instance, if I create a struct, so I call it, I'm gonna call it like user, for instance, and then I have a static property on user. What could it be? Could it be, for instance, I don't know. What could make sense? Like something that would be common to all user. Maybe like a prefix when you store it in some kind of database. So it would be like user underscore, just for the sake of an example. And now let's see. Do we have a key path to this thing? In a way, I would say that no, you don't have one because since you call the key path on a value of the type, then you couldn't call it on. I mean, you would need to have like call it on the type itself. Or what if I do something like that to kind of refer to the type itself? Doesn't work. Yeah, key path cannot refer to static member prefix. So if it were to exist, it would probably be this syntax where you say, okay, it's the type, then I'm referring to the type itself and not an instance, and then the property prefix. But there is no key path for a static property, which in a way kind of makes sense because there wouldn't be that much of a use for it. Anyway, if you need to like, you can always pass in a closure. So there are no key paths for static properties. And now let's see for the case of async stuff. So for instance, we're going to create a new var. So it's going to be like that. It's going to be async stuff. I never remember where you should put the async. I guess it's before that you put it. It's just going to be a string. And so here, since it's async, we're going to do like task.sleep. No, it's not that the syntax. So what could be the syntax like that? No. Maybe like that. I'm gonna just do a quick like Google search to make sure. So if I say so, Swift computed property and async. How to create and use async properties. Okay, so it's more subtle than that. So you do a property just like any other property, and then you say, okay, getter is async, and then you can do yes. Thank you. Thank you. I see you've given the answer also in the chat. So it's like that. And so here, for instance, I'm going to do task.sleep for a duration of like 1 second. So it's going to be probably like a wait. Maybe I will need to also deal with the error. We'll see. And then I will just return like hello, something like that. Let's see. Does it build? I also need to do like try. I'm going to do something like that. Okay. try must precede await. Even though it's just a warning, I'm gonna take care of it. And so now let's see. When I have a user, so I can refer to async stuff, and let's see if we can call it. So I'm just gonna have my user, gonna call it like that. No, you can't. So you cannot form a key path to property with throws or async, which in a way kind of makes sense because then like the whole syntax around calling a key path would have to become much more complex to deal with the potential error or the potential async. So that was a very good question. And so key paths, you could say it's just for property who are synchronous and that never return an error. And this limitation kind of makes sense because it allows for a nicer and simpler syntax when you are using key paths. So I can understand why they would implement it like that. Let's see. And then, oh, good remark. If you have a dynamic member lookup type with a string literal subscript conformance, you can have arbitrary key paths. So yes, then you will be able to have arbitrary key paths in that case. You know what? I'm gonna try and implement it because it feels like a good example, even though it's gonna be a bit more complex. So let's say I have my user. I'm just gonna get rid of this, and so I'm gonna do dynamic member lookup. You know what? I'm just gonna use Google to say like Swift dynamic member lookup key path, because the syntax, if you don't know it, it's a bit okay. So it looks like that. So first I would need to annotate my type with @dynamic member lookup, and then I need to implement so this key path, this subscript right here that takes in a key path as its argument. Here the key path, it will be maybe something of type user, so something like that. And then, oh, because then I'm calling the key path, yeah, because I'm taking some code off from the internet, so this is a little bit less prepared. Just trying to find an example. I'm trying to find an example where it would be plug and play so that I can show it to you. I'm finding the proposal in Swift that introduced this. Okay, I might have a good example. Okay. Yes, so this is a good example. So this is coming from an article from Antoine Vanderly. And so what he's doing is that he's creating a struct called notification wrapper, marking it with @dynamic member lookup. So it's wrapping a notification. And then he has dynamic member so that he can query the user info of the notification. So how would it look like? It means that if you want to create a notification wrapper, you're gonna create it like that. How do you get a notification? I'm gonna take like an already existing name. Let's see. Something like that. Will it build? Okay, it didn't syntax following didn't work, but it seems it's valid. And so now on the notification wrapper, so for instance, you can say like you can basically call anything on it, and what you type here is turned into a string and gets passed to this function right here. So it's nice when you are dealing with something that is already stringly typed under the hood, but it's important to be aware that this kind of gives you like the illusion of type safety, even though you don't have it. If you make a typo and you type and you refer to something that doesn't exist, the compiler will not warn you about it. And so it seems we could also like combine this with key paths somehow. And I'm trying to understand. Oh yeah, oh yes, now I get it. Now I get it. I remember it now. So I'm gonna just remove this code and put other code from the article. So you have here a struct that is going to be nested into another struct. So we have this struct blog, and you have two property on the blog, a title and the URL. And then you have a blogger, which is the name of the person, and then his blog, so his article. And then by doing this subscript that takes a key path, you're able to reroute the key path you're receiving into the blog property. And what this allows is that, so I'm gonna create a blogger. So let me create one. So for the name is gonna be Vincent. For the blog title is gonna be something about key paths. So I'm gonna try and make it pretty, something like that. Okay. For the URL, let's do URL from string, like this one, and I'm gonna put my website with vincent.com, something like that. Okay. And so now what you can do that is pretty cool is that on this object, you can do dot title normally. Let's see if it works. I just need to unwrap this. So you can see it works. I've been able to call the property title on the blogger, even though there is no such property on the blogger. And what happened is that when I called title, it was turned into a key path to the property title on a blog, and it was routed to this method subscript, which under the hood invoked the key path on the blog. So it's an interesting way to kind of like when you have nested things, to make all the properties of the nested things available on the host, you could say. It's also syntax that can become very tricky, because then if you have the case where there is the same property in two nested values, you will get a conflict. So I would say it's good to know about this. However, I wouldn't recommend using it like left and right without thinking about it. A way where it could make sense is, for instance, if you are implementing a framework level code and you want to expose a nice API that doesn't reveal too much of the underlying structure, and you also don't want to implement by hand all of the like boilerplate that just calls under the hood the property of a nested value, you can automate it with that. So in a way, it's a form of code generation. You can see it's something that is similar to code generation. So it's useful when applied at the right places, but just like code generation, you don't want to apply it left and right, because it's going to get you into trouble, in the sense that it will make your code harder to read because unexpected things are happening. Okay, I see a few comments. I think I'm going to keep moving, because otherwise this is going to last way too long, given that I still have a few additional pages in my playground. So let me remove just this code so that we are with what I had initially planned. This way hopefully the playground won't be crashing on me. And let's move on to the next page. So page number 2, standard library continued. So we're gonna do basically the same thing than before, just going with more complex functions. So this time you can see I've defined a struct person. So a person has two property, and a name, which is a string, and an age, which is an int. And then I'm creating an unordered array of person. And so what I want to do is to sort this unordered array. For instance, I want to sort it by increasing age. So in Swift, we already have everything we need to do that using closures, using this time comparison closures. So we have the function sorted by, which takes a closure that takes as an argument 2 elements of the array. And in the closure, you say if the 2 elements are in increasing order or not. And so here, since we want to compare the property, we want to order on the property age, we compare the property age on both values. But it would be pretty nice to implement a version that works with a key path, where we could say, okay, I want my array sorted by \age. That would be nicer than a closure, and also it would be less repetitive because we wouldn't have to mention the property age twice. So let's see how we could make it work. Let's look at the closure that the method sorted by takes as an argument. Its signature is element element, 2 words bool. So it takes 2 elements and it returns a bool. How do we go from a key path to this signature? So I want to implement this method, this function rather, that I call there. You will understand the name when you see my goal syntax, because I want to be able to say unordered sorted by their age. That's why I chose this name for the function. But what's important to understand is how the function works. And the function works by taking as an argument a key path, as you can see in my example of how I would use this goal syntax. So it takes in a key path. You can see the key path as an argument to the function there. And the function there returns what the method sorted by expects. So it returns a function that takes 2 values that are the type of the root of the key path and returns a Boolean. How can we implement the method theirs? So here, once again, if you're watching the replay, maybe make a little pause and try to implement it yourself. You can follow the same strategy than what we did for the get function, which is to follow the signature and see where it leads us. So here the signature says we have to return a function. Let's return a function. This function takes 2 elements. So very often for comparison function, they will be called LHS and RightHS. This stands for left-hand side and right-hand side. So left-hand side of the comparison, right-hand side of the comparison. And how can we compare these 2 elements? We can get their value using the key path. And since the value will be comparable, then we'll be able to use a comparison operator between the 2 values. So let's get the 2 values. Let's get the value on the first argument on the left-hand side. So we pass in the key path. We do the same thing for the right-hand side. We pass in the key path also. And so we have now our 2 values that are comparable. And so we can use a comparison operator to compare them, which will return a Boolean. And that's it. We've written the implementation of the function there. And so now I can try and use it. I will run the code. We'll see what will happen. So I said I wanted my unordered array of people sorted by their age. And you can see that indeed it works. The elements in the array are sorted by their age. So this is quite an interesting example, I find, because it shows that you can build some really nice ergonomics, I would say, in the sense that this is not a game changer, but it's a nice way to have a syntax that is a little bit shorter, also a little bit more descriptive, in the sense that this reads like plain English. I want my unordered values sorted by their age. And as with most of what we are going to implement in this training course, you can see it's rather easy to implement. If you have the idea of how you're going to go from the key path to your goal function, then the implementation is pretty straightforward. In that case, we could also introduce a custom operator to shorten it even more, like I did with the little caret operator just before. But I would argue in that case it's a pretty bad IG because here the name of the function actually helps with the readability. And so for this kind of cases, I would definitely encourage you to keep a full name and not try to do something like this, which would, I would say, look weirder and less readable than just having the name of the function spelled out. Now let's try and go even further and try to sort on more than one attribute, because maybe I would like to say, okay, I want to sort by their age, but when the age by increasing age, but when the age of two people are the same, then I want to sort by either increasing or decreasing name. Right now with our syntax we cannot do it, but we're going to implement it. And so we're going to implement it in several steps. First, we're going to implement what I call a naive version of it. You will understand why a little bit later. So I want to implement a method sorted on my sequence that will take more than one key path. You can see it will take more than one key path because I'm adding the dot 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 after the type of the argument, which turns it into a variadic argument, meaning that you can pass several arguments separated by a comma, and then inside the function, this argument will basically you will be able to handle it just like an array. I see a good remark being made on the chat. You can declare an extension on key paths. You don't even need the custom operator. That's a very good point. If that makes more sense for the syntax you want to achieve, indeed, you can create also extensions on key path, because as we saw, key path is just a type, is just a class, and so like with any class, you can create extensions to it. So this is the syntax I would like to have, being able to say, okay, unordered, sorted by first the age, then the name. So let's try to implement this little function. And this time I'm gonna have a look at the finished version because this one is a little bit harder to implement. So let's go ahead and implement it together. So this time just following the signature won't be enough because there is a little bit of sorting logic involved. But for the beginning, we can still have the same approach, which is like, okay, let's call the sorted method that the standard library already gives us. So where we pass in a closure that takes a left-hand side and the right-hand side. And then the way to implement this sorting is to say, okay, I want to iterate over all of the key paths in my key paths argument. So here I'm receiving one or more key paths. I want to iterate over them. And then I want to use the key paths to get the values in order to perform a comparison. So on the left-hand side, I'm gonna get the value using the key path. Same thing for the right-hand side. I get the value, the comparable value using the key path. And then what I'm gonna do is that if for the left-hand side, the value is greater than or equal to the right-hand side, I'm gonna return false. So I'm gonna say they are not in increasing order because I have found a property for which they are not in increasing order. Else, so if I've been able to go through all the key paths and all the properties were indeed in increasing order, then I will return true. So this code allows you to sort in increasing order using more than one key path, so using more than one property. However, if we try to use it, we are going to see a very interesting error. You can see it says key path value type string cannot be converted to contextual type int. It's because we are passing two key paths that have the same root, but not the same value. Age has a value of type int, and name a value of type string. And even though both int and string are comparable, you can see that they are obviously not the same type. And here in my sorted method, I say that I have one singular value generic argument, and I expect all of my key paths to use the same value. And so since the first key path had an int for the value, then the function, the method expects the second key path to also have an int for the value, and so I have a problem. So this syntax, even though it's correct, won't work when we want to use key path that refers to property of different types. However, we're going to solve this problem, and we're going to solve it through a trick that's called type erasure. And the way this works is that we're going to rely on the fact that in order to call the key path, you need to know what the root is, but the value, you only need to know it when you make the comparison. And using this, we're going to be able to come up with a syntax where the sorted method only needs to know about the root, and the value can be omitted from the signature of the sorting function. This might seem a bit weird, and rightfully so, because type erasure can be a bit confusing, but as we go into it, you will see that it will all make sense. So we'll need to implement a little bit more code. I'm gonna need to write a way to encapsulate a comparison operation. So I'm creating this sort struct, which takes a generic argument, which is an element, and my sort type, basically, under the hood, it stores a comparison function. So a function that takes two elements and returns a comparison result. I see a very good question about any comparable. We'll try it just a bit later. If it works, it will be great, because it will be even better. But I want to show this version because this version has the advantage of really showing what type erasure is. But you're making a very good remark. I want to get back to it just after. So what's a comparison result? It's an enum where you have order ascending, order same, order descending. So kind of the same than returning a boolean to see if they're in increasing order. There are just a few more cases, but it's basically just a syntax difference. And I'm creating a static func that I will be able to call on my type that will return an ascending sort. And so I want to pass it a key path to an attribute of my element, and it will return me a sort. So something that can be called with two elements. And what's interesting is that, as you can see, the element, so the root, is being declared at the level of the struct, but the comparable property, so the value, is only declared at the level of the static function. That's what I was saying when I said we only need to know the actual comparable type when we do the comparison, but then for the rest, we can rely on the fact that the comparison returns either a boolean or a comparison result. So how can we implement this ascending static function? We are going to return a sort, and so this sort will take as an argument a compare function, which will have a left-hand side and a right-hand side. And what we're going to do is that we're going to get the two properties, so left-hand side property and right-hand side property. We're going to get them by calling on both the left-hand side and the right-hand side the key path we're given as an argument. So like that, and then right-hand side attribute, so like that. So I'm using this tuple syntax just to do the thing in one line, but it's the same thing as if you had done let LHS property equals this and RHS property equals this. Just made a small typo here. And then we're going to do if left-hand side property equal right-hand side property. Then we're gonna do, okay, it's ordered same. Else if left-hand side property is less than right-hand side property, then it's ordered in ascending order. Else, then by elimination, it's ordered in descending order, like that. And so now that we have our sort type, we can implement a new version of sorted by on sequence, which this time takes a number of sorting criteria. So before it was taking a variadic number of key paths, now it's taking a variadic number of sort. And under the hood, it's implementing the same logic than before. It's iterating over the sort criteria, and for each sort criterion, it compares the two elements using the criterion. If it's ordered the same, it just breaks and goes on to the next one. If it's ordered ascending, it returns true. If it's ordered descending, it returns false. And now we can use our syntax. So we can say, okay, I want my unordered array of people to be sorted first by ascending age and then by ascending name. And you can see that in the case where there were two ages equal, then the elements were sorted according to ascending names. Of course, we can also implement descending sort. So we need to implement a different function, static function on sort. So we implemented ascending. We're going to implement descending. So descending, how does it look like? It's actually basically the same thing than ascending, just we change the order. And so we say descending when we meant ascending and ascending where we meant descending. And now we can say, okay, we want sorted by ascending age and then descending name. So let's see how it looks like. You can see that it works, but we can also say, okay, descending age and then descending name. So let's see. So you can see descending age first and then descending name, and then let's do ascending name just to make sure that it also works. And you can see that it also works. Did you mean continue instead of break for ordered same? Good point. I'm wondering whether when you are in a for loop, whether oh no, I think it's break. I think it would have done probably the same. So break is going to get us out of the switch, and since there is nothing else in the switch, then it goes onto the next loop. So I guess continue, if there had been like other code here, if there had been like something else here, it would have skipped this extra code. But in the special case where there is only a switch in the for loop, I would say that continue and break, they are kind of like equivalent in that special case. So you can see that it works. And now I can go back to the very good remark that you made, Prof. Amesh. Can't you use keypath value any comparable as the parameter type? So any comparable, was introduced later in Swift than keypaths. So actually, I'm not sure. We're going to try and see. So let me go back to here. And so I'm going to remove my generic argument here. Instead, I will say any comparable. Let's see. Does it still build? Then it says here, type cannot conform to sequence. Let's try and understand why we would have this issue. Maybe I need to do self dot sorted. So we have an error, which is not super clear. Usually this kind of cryptic errors is because we've done something that messes up the type checking, but in a way where the compiler, okay, it's because it's unable to infer a closure. Okay, so maybe actually I could just say, okay, this is an element, this is also an element. Let's see if it helps. Oh, and then when I do that, I need to put parentheses. Okay, and now it says binary operator cannot be applied to any comparable operands. So it seems that at this point, we have lost the fact that both properties are comparable, but the compiler doesn't know that they are comparable of the same type. And which kind of makes sense because when I invoke the key path, in the eyes of Swift, even though it's the same key path, but it could be different type of comparable actually. Because yeah, actually the key path could return like it could be like a property that says, okay, like one out of 2 times I'm going to return an int, the rest of the time I return a string. And let's see if some could help, but I don't think so. Yeah, no, you cannot use it here. So actually, it seems that any doesn't work because the compiler isn't able to prove that this here is of the same type than this here. So it seems that in that case, any doesn't work. And so even with the addition of any to Swift, we still need to implement this kind of additional boilerplate if we want to do advanced sorting using key paths. So like with other examples I've showed you, the goal of these examples is not to advocate that you should be using this kind of syntax in every single project. It's more to show examples of what can be achieved with a key path, the kind of functions you can build with key paths. And my goal is that then when you find in your apps, in your code base, a problem that can be solved efficiently with a key path, you can use these as examples to implement things that make sense for your own apps. Don't try to shoehorn this code because it might very well not work. It might very well just make your code base even more complex. And you were saying, I just want to try it. So you were saying, let's make any key path. Since key path is not a protocol, it's not sure it's gonna work. Yeah, because key path is not any has no effect on concrete type because for Swift and here is still the problem that comparable is any comparable implicitly, and so actually it's the exact same problem than what we had before. So it was worth a try. It was a good point that you raised, but it seems that that Swift cannot do that yet. Actually, to implement this today, I would use parameter packs, which is what Swift 5.9 will bring. And with parameter packs, I think it would work out of the box. However, as of the moment where I'm recording, you need Xcode 15, which is still in beta, and I'm not running the beta, so we cannot try it. But it could be a nice exercise to try and use parameter packs to implement what we've implemented. Okay, let's move on to the next page, and we're going to build something that is maybe something that you might find more use cases for, and also it's kind of interesting to talk about it today because Swift very recently and through its new macro system has implemented something that is quite similar. So we're going to talk about type-safe predicates in this third page of the playground. And so before we talk about type-safe predicates, I want to bring you back to the glorious days of Objective-C, where we had not type-safe predicates. We had stringly typed predicates. So in Objective-C, if you had a class called person, and on this person a property of type age, and then you had an array of person, you could create a predicate using NS predicate. You would pass in a format, and so it would be a string where you say my predicate is that the property age is strictly greater than 18, and then you could filter your array using that predicate. So if we take a look at it, we can see that we have now only 3 elements. So we have this one, and this one, and these two here have been removed. So this was great in Objective-C, but it had the downside of being stringly typed. So there might have been indeed syntax where you could use hashtag keypath in order to get something that was type safe, but still under the hood it was not type safe. And until very recently, Swift didn't have a built-in way to express key paths. This is changing a bit now because Swift data relies a lot on predicates, as any data manipulation framework would. And so I want to show you how you can implement a type-safe syntax for predicates in Swift using key paths, and we see that it's much easier than what it would seem. You just need to have the right ID, and from that, it's pretty straightforward to implement. And before we go any further, I also want to make sure I define the term predicate, because I've been using it, but if you've never heard it, it might seem very cryptic. A predicate is basically a function that returns a Boolean. And so it's something that is used typically when you want to filter some kind of data collection. And so here, the predicate we create, it takes as an argument an age, and it returns true or false because every predicate returns a Boolean. So a predicate, it's basically a function that returns a Boolean. So let's try and make it work with Swift. I would like to be able to write this syntax right here to be able to say, okay, I want an array of people, which this time will be containing Swift structs, and I want to be able to say, okay, I want to filter my array, and my condition for filtering is that the property age must be greater than 18. And I want this entire syntax to build in Swift. And so that's what we're going to build together. So first, we need to implement something to represent our predicate. So I'm implementing this struct that I call predicate. You can see it's a generic struct. It has a generic argument that I've called element. And inside the struct, I have what I have called an evaluator, and it's basically the function that will evaluate the predicate. So it's a function that takes an element as its argument and returns a Boolean. And you can init the evaluator, init the predicate by providing it with an evaluator, and you can evaluate with the element. So this is just a way to have a type that wraps the predicate and has a nice generic syntax around it. And also, I could have used like row closure, but then we would have ended up with a function that would have closures everywhere in their signature, and you will see that being able to say predicate of element in a signature really helps have code that feels cleaner. So now, how do we implement this syntax? If we take a look at it, this expression right here, at the center of it, we have a comparison operator. And as it turns out, making this syntax possible in Swift is as simple as implementing an overload of this comparison operator. So I'm going to implement an overload of this comparison operator, and this overload will take on its left-hand side, so on the first argument, a key path. That's what I have here on the left-hand side. And on the right-hand side, it will take a constant. And as you can expect, I will want the type of the constant to be the same type than the value that I can get by using the key path. And so let's implement this. So I want to return a predicate. So let's return a predicate. The predicate, it takes an element as an argument. I need to return a Boolean from it. How can I return a Boolean? The only way is to compare two things comparable here. And so I'm going to take my element. I'm going to invoke the key path on it. And then I'm going to say, okay, is it greater than the constant? So basically, I took the operator and I pushed it down inside a predicate. And to build the predicate, I used the key path to query the element and compare the value of the given property that the key path refers to the constant that I've also been given. And so now we are almost there. We just need to implement the filter function that will work with a predicate. This one is pretty straightforward to implement because it's the same strategy than before. We just use the built-in filter function, which takes an element. And how do I know if the element is included? I take my predicate and I evaluate it with my element. And so now I've created my array of person. So I'm still using the same object, the same class with an Objective-C property, but actually we can turn it into a struct and remove all traces of Objective-C from it. This way we can make sure that we are using pure Swift. And so I can run this code. Let's see, did it work? So I had my original array, and as you can see, it worked. The type safe predicate syntax worked. So I've been able to write this predicate, and this predicate expresses the fact that I only want to keep the person whose age is strictly greater than 18. And so indeed, the two persons that had an age less than or equal 18 have indeed been removed from the array. So personally, I find something that is pretty cool because it's super powerful and the implementation of it is quite simple. You just overload an existing operator. Now in modern Swift, this syntax will be a little bit less useful because there is finally a built-in predicate syntax that was introduced along with Swift data. But if today in your code you are manipulating data quite a lot, you might be interested in taking a look at this kind of approach because it just makes your code, I would say, slightly nicer than when you are just passing a closure where you would say, okay, $0.age is greater than 18. So it's kind of cool, but now let's try and make it even more complex. Let's try to combine two predicates together with the operator AND. So let's try to implement this. So this time the operator will take two predicates and return a new one. So let's try and implement this new operator. So once again, we want to return a new predicate. So let's do that. This predicate will be evaluated for an element. And how do we evaluate predicate on the left and predicate on the right? We take the predicate on the left, we evaluate it with the element, and then we do an AND, and we evaluate the predicate on the right, and we evaluate it with the element. I see a very good question. Is the predicate struct necessary? So no, it's not necessary, since the predicate is actually just a closure right here. You could replace the predicate with a closure. You could do that, actually. That would work. However, I would say it gets slightly harder to read. So having like the predicate, I find that it's slightly nicer. Also, I don't have a really strong opinion on it. If you would prefer to just like pass in functions, that would also make sense to me. So we've implemented the AND operator between two predicates. Then we need to also implement another comparison operator so that this syntax right here can become possible. So this time implementing the strictly less than operator is going to be very easy. Actually, I can just take the code of the strictly greater than operator, just paste it, and under the hood, replace which comparison operator is being used. And so I'm just missing, oh yes, I added one too many predicate. Very true. I could also get the best of both worlds by using a type alias. That's also very true. Yeah, that's a very good remark. And so now, with these two new operators, this is going to work as expected. So I'm going to filter and only keep the person whose age is strictly greater than 18 and strictly less than 80. And so if we look at the array, we can see that there is one here, a second one here, and that's it. And so indeed, we only have these two people left in the array. So that's pretty cool, but we can go even further. We can implement pattern matching, so where we can switch over a person, so over a value, and then in the cases of the switch, just write a predicate. And as it turns out, in Swift, that's quite easy to implement. What you need to implement pattern matching is this operator, so tilde equal. And what can be a bit confusing is that the left-hand side of this operator is what you will find in the case, and the right-hand side is what you will find in the switch. So it's a little bit weird, but once you wrap your head around this, then it works pretty well. So let's implement the operator. So I'm given an element and I need to return a boolean, and I also have a predicate on the element, so it's very easy. I just take the left-hand side and evaluate it using the right-hand side. And so if I create this kid and I switch over it, I create a case when the age is strictly greater than 70, a case when the age is strictly less than 18, and if I run the code, you can see that indeed the code is being executed as expected, and so the second case does match. That's also pretty powerful to see that you can switch over a value and in the cases use the type safe predicate that we've implemented, because in a way it allows you to kind of like extend Boolean expressions in Swift with this custom syntax that we've just put together. So that's pretty cool. If you're interested in using this in production, I have a framework ready for that on GitHub. I haven't put the link on the description, but I will add it once the live is over. It's called KeePathKit, and it can be also interesting to see how it's implemented. Just keep in mind that Swift has implemented its own predicate system now. So it's available in Xcode 15 beta, but Xcode 15 will be out very soon. So when you are watching this, if you're watching the replay, it's more likely than not that Xcode 15 is already been released. And so you might want to look at how these type-safe predicates work in Swift data. What's interesting is that they don't allow you to use any property. They use the macros, and the macros only allow you to call certain properties on your data structure. So for instance, on a string, you can call maybe like prefix, suffix, but you cannot do like any arbitrary operation, which makes sense because since the predicates are being used by Swift data, and so a database under the hood, you want to make sure the database first can implement the operation, and also that it's operation that can be like run in a reasonable time. So we are making progress in our understanding of key paths. By now, you should have a pretty good understanding of how key paths are and how they can be used to build more complex syntaxes. If you use SwiftUI, you probably use the environment, and you probably know that the environment relies a lot on key paths. Actually, since iOS 17, it relies, I think, almost entirely on key paths, because the notion of observable object has been removed. And so my hope is that through this example that I've showed you, now you have a better understanding of how something like the environment in SwiftUI has been built using key paths as the interface that developers are using when they write SwiftUI code. But we are not done yet. We still have a few things left to do. So we're going to try and keep pushing the limits of this type-safe syntax. And so this time we're going to try and do something that is like very like database-like. We're going to try and do a join between two arrays. So I have a first struct person, and then an array of persons. Then I have a struct login, which records the moment when people have logged in into a system. And you can see that I have the ID of the user that logged in, which refers to the ID of the person. So this is what database people call a foreign key. And I want to implement a join operation. So I want to join my array contacts with my array logins, where the ID of the contact is the ID of the login. And so I would be able to have a tuple where I would have, okay, so this login corresponds to this user, this login is matched to this user, and that login matched to that user. And so we'll try to implement it because it's a way to see, it's a good example to see how we can build even more complex things using predicates. So this time we're going to need to use what I've called here a double type predicate. Why double type? Because even though the values of the properties referred to by the two key paths will be of the same type, so here they will both be of type int, the roots on which the key paths will be called will be different. Here, the first root will be a person, the second root will be a login. And so we need this double type predicate, which takes an element and an other element. And for its evaluation function, it takes two elements and returns a Boolean. So actually, I've called it a double type predicate just because I already have a predicate type, but a predicate in math can have as many arguments as you want. Often it will have only one argument, but a predicate can have 2, 3, 4, 10, 1000 arguments. It still is a predicate. So the logic for double type predicate is the same than for the regular predicate, just a wrapper around a closure. And so now the question is, how do I implement this equal operator right here that takes the left attribute of the join and the right attribute of the join? So let's try and do it once again by following the signature. So I need to return a double type predicate, okay, where I have my first element and my second element, like that. And now I need to compare these two things. I need to produce a Boolean from these two things. So from the first element, I can use the left attribute. So actually, the name left element will be much better, and right element, this way, it will be like the naming will be the same between the two sets of arguments. So I get the left attribute of the left element. I also get the right attribute of the right element. So like that. And to compare them, I'm just going to do equal. I can do it because they are both equatable and they are both the same type. You can notice that I have two different generic arguments, one for each root of each key path. However, the two key paths share the same generic argument for their value. That's why I'm able to use equal between the two values that have been retrieved by invoking the two key paths. And actually, that's it. I've implemented my equal operator. That was easy because the strategy is still the same than before. We are just creating a wrapper around the existing equal operator, except that this equal operator operates on two equatable values, and here this equal operator operates on two key paths that refer to an equatable property of the same type. And now for the other part, for the little bit trickier part, we need to implement the join method. So I'm having a look at the finished version because this one is slightly more complex. So I'm implementing this on a sequence. I want to join my sequence of elements with a sequence of other elements where a predicate holds, and this predicate will be called, will involve elements, an element of the first sequence and an element of the second sequence. And it will return an array of tuples where the first element of the tuple will be the element of the first sequence and the second element of the tuple, the element of the second sequence. And so the way to do it, so actually, how you implement a join in databases is quite an interesting problem because it's something that you want to do fast. So databases, they are very very advanced ways to implement join operations. They use indexes and all these kind of things. Here we're going to implement the naive implementation, which uses a Cartesian product. So meaning we iterate over every pairing that we can do between elements of the two sequences, and we see whether they satisfy the predicate. It's not the best because the complexity of the algorithm is quadratic, and you can get much better by using indexes. But it will do here because the goal is not to get performances, but rather to see how to use key paths in some complex use cases. And so what we're going to do is that we're going to create an array result. So it will be an array of the type that we want to return. So an array of tuples of elements and other elements. We give it an initial value of the empty array. And then we start iterating. So we say for left value in self, so in the left sequence, in the sequence that is on the left side of the join, we iterate over the values. Then for every value on the left, we go over all the values on the right, so on the other sequence. So here is going to be this argument, which I should actually call other sequence. The name will be a bit better like that. And what I do is that for each of these matching, I will say, okay, is my predicate evaluating to true for that matching of a left value and a right value? If that's the case, then to my array result, I append a tuple that will contain my left value and my right value. So the algorithm is rather straightforward. And once I'm done, I'm just going to return my array result. Yes, so very good question. Is equal a function name? You can understand it indeed as a function name. This syntax looks a bit weird. It's the syntax to overload operators. So there are in Swift there is a finite set of characters that you can use as operators. Equal is one of these characters, or rather, like it's two characters, but in a way it's a word, we could say. But I think you get what I mean. There are in Swift there is a finite list of composition of symbols that can be used as operator. Equal is one of them, and so the way that you overload an operator is by implementing a function, and instead of the name of the function, you write the operator. And then if your operator is an infix operator, so an operator that you use in the middle of two operands, then by convention, the first argument of the function is the left-hand side, the second argument the right-hand side, and then the return value is what the expression that your operator implements evaluates to. So it can be a bit confusing, but once you wrap your head around it, you'll see that it's purely a convention. And so we are almost there. So it's not working, probably because I have missed something. See, it says like expected closing parentheses, so I've missed something somewhere. Maybe you've already spotted where you've been faster than me. Not in the if here. Oh, I think actually it's here. Yeah, it was just here. Let's see if it works. Cannot infer key path type. Oh, it's because I've called it, no, it's called join with. Okay. Oh, it's this because there is a dot here. Why is there a dot here? Let's remove it. This syntax is super weird because I don't even want this, like, join where. Okay, it should be just something like that. I don't know what happened. Okay, so let's see whether it worked. So we can see indeed ID4 user ID4, ID5 user ID5, ID7 user ID7. So we've been able to implement this this join operation. Once again, I don't necessarily advocate that you should use this in your code. Actually, don't use this algorithm. This is a join algorithm that doesn't scale at all. What I wanted to show you is that with key paths, you can implement even more complex things. And I wanted to show you the case where we use two key paths and then we build expressions using the two key paths that come from two different objects, because it's very possible that in your apps, in your code base, you have situations that match the same kind of problem. And so I wanted to show you that it's possible to solve these problems using key paths, because you might have some use cases for it waiting in your apps, in your code bases. Operators can avoid return types too. Yeah, that makes that's a good remark. Some operators, but these, so you say operators can avoid return types too, but then I would assume that these operators would also be like either mutating or take an in-out argument, because like they need to the effect of the operator needs to happen somehow. But that's a very good remark. Okay, that's all for this page. Let's move on to the next page. So this one I want to show you. A pattern that you can implement using key paths, and it's a pattern to be able to validate properties on a value. So I'm going to show you what I want us to implement. Something like this. On a user, we want to add predicates. So a first predicate, a second predicate, and then we want to validate, meaning we want to check that all the predicates indeed evaluate to true. So it could be useful, for instance, if you have a form to build a complex object and you want to make sure that a set of rules is indeed satisfied before you accept the object as valid. And so let's try and build this syntax. So I've copied and pasted my predicate type from the previous page because we're going to use it. We are also going to need our equal operator and our AND operator. So I'm just going to re-implement them real quick, but the logic here is still the same. So we create our predicate, we have the elements. So for the equal operator, we get the value using the key path we've been provided, and we checked whether it's equal to a constant. Okay, that works. And for the second one, how to combine two predicates using the AND operator. So we create the new predicate like that. We have the elements. We evaluate the left predicate with the elements, and we do a AND with the evaluation of the second predicate, still with the elements. So this is the same code than what we've done before. Now let's get into the meat of the topic. So we have this struct called validator. You're going to give it a generic argument element, and it's going to store two things: a valid, so the value that you want to validate, and a predicate, and a method validate. What we do for the method validate, we call the predicate and we evaluate it with the valid. And then we're going to create a protocol validatable that will be implemented by the types on which we want to be able to add predicates and then evaluate them. So once we have this protocol validatable, we're going to want to have a method that will allow us to add a predicate on an instance that is validatable. So how can we implement this? So let's try and do it together. And the strategy we're going to have here is going to be, once again, the same than before. Let's just follow the signature. So I want to return a validator that is a validator of self. So a validator of whatever I will call the method add on. So if I call it on a user, it will be a validator of user. So let's implement this. So I'm gonna return a validator. Okay, like that. It needs a valid, so it's going to be self, this time with lowercase s, so it's going to be the instance on which the method has been called. And then it needs a predicate, and so the predicate, I have it, it's what I've been given as an argument, what will be built using the literal syntax that involves closures. And then we're gonna need a method add, but this time not on validatable, but on validator. Because here you can see the first time we call the method, it's on a validatable value. But then the second time we're calling it on a validator itself. And so we want a way to be able to chain validators together, kind of like the way that we chain modifiers on a SwiftUI view. So let's also implement it. So we need to create a new validator. So the valid is still self. So no. Is it still self? Still self? No, because now this time validator, actually, self refers to a validator, not a validatable. So I cannot use this syntax. Instead, what I need to do is that I need to access the valid of the validator. So this thing right here. And for the predicate, I'm going to need to build a predicate. And how I will build it is that I will be given my elements. First, I will evaluate the predicate that is already stored in my validator. So the one I built with the first call, I'm going to evaluate it with my elements. And then I'm also going to evaluate the second predicate, the one I've just been given as an argument. I'm also going to evaluate it. And so what I do is that I say, okay, first I'm going to evaluate this, then the next potential predicate, etc., all the way up to when I reach the call to validate. And finally, the method validate is just going to call the predicate, and under the hood, the predicate are linked together. So what we've implemented here is kind of like, in a way, it's kind of like a linked list in a way, except that instead of having a reference to the next element on the list, we have the AND operator that allows us to combine two elements of the list together. So I was saying it's kind of like a list. To be more precise, it's kind of like a reduce being called on a list. And so now with this, normally, this should work. So I have my struct. I've made it validatable for an extension. I've also created two instances that conform to my struct. And so I could try and run my code. And you can see that in the first case, so validate yields true. Actually, I'm going to show it so that you can make sure of it. So it writes it there, but it's really like the value that is here. And so what it does is that it takes all the predicates I've added, and then when I call validate, it evaluates all of them. So the syntax, I mean, the implementation is quite short, but also quite simplified, because in a real implementation, you would like to know which predicate has failed. You would like maybe the failed predicate to have a custom error message, this kind of things. Maybe you would like to also execute a closure, a different closure for each predicate. For instance, if a predicate is associated to a field in a form, you would like the scroll to scroll back to that form. But the general idea of it is here. And once again, my goal here is to show you examples of what can be built using key paths. I just want to really drive the point that I'm not advocating that you put into your project all of the examples I show you. It's more about showing you how to build things using key paths, because if you know how to build things using key path, then it becomes so much easier to understand how things that have already been built with key paths, like SwiftUI, like SwiftData, it's much easier to understand, to get a sense of how they work under the hood. So you're saying, so Swift is not a case-sensitive language. If you can elaborate a bit, I would be curious about what you're referring to actually, because Swift, as far as I know, is indeed case-sensitive. So feel free to let me know. I think there is a slight delay between the chat and the live. In the meantime, that was all for this page. So we're getting close to the end. Now we're going to move to the last example. So pages 6 and 7 are the same example. We're going to talk about how to implement data binding using a key path, because it kind of like, I think it's a good example to getting a sense of how SwiftUI works under the hood, at least on the conceptual level. As you can see from the equal imports here, I'm importing UIKit. I'm importing Playground support to display a UIKit view in the Playground. So if the Playground is going to crash or have issues, it's probably going to happen now. But before, let's go back to the previous page. So you're saying equal created function name. So this indeed here is the same thing than here, but I don't see where case sensitivity comes into play. Actually, feel free to elaborate in the chat, and we can always get back to it together, because I'm sure you have a very good point, and I would really want to make sure that we get to the bottom of it. But in the meantime, let's go back to the next page, and let's imagine that we are working in an app implemented using an MVVM architecture. So it's a UIKit app, and we want to implement data. It means string comparison string comparison. So string comparison, I think string comparison is case sensitive. Let's see. Yeah, now it says false. So yeah, so string comparison is case sensitive. Did I cover array, dictionaries, and key paths also? No, I don't think I will cover them. I think, however, in the links at the end, yes, I have the link to the proposals that talk about these examples, because these are good examples, but they are quite advanced. But I will just say it so that people can know about it. But you can take a key path to like an element in an array. I'm just going to write it so it makes sense. So I have my array here, which is going to be like 1, 2, 3, for instance. And then I can take a key path. So it's going to be a key path that has for root an array of int, and the value. How do you write it? I never remember how you write it, if it's like that or not. Okay, so I think it's indeed the good syntax. Then I can say array key path, and then just pass the key path. And so, as you can see, this key path refers to the second element of the array. So it's an interesting possibility. To be honest, I've never used it in production code. And the reason why I didn't want to cover it and rather let people read the Swift evolution proposal for key path that covers this is because this brings in a lot of interesting questions. For instance, when is the element? Imagine that you chain things together, and so you have first a property, then an element of the array in the property, then another property. It begs the question of when is the array evaluated? Is it evaluated when the key path is created, first invoked? I mean, there is a lot of interesting edge cases that I don't want to go into. But good point to mention it. You can take key paths for elements in arrays and dictionaries. And if you want to learn all the details about it, there will be links in the last page of the playground with them. And yeah, definitely agree. The first time you see it, it's kind of like black magic. To be honest, I learned about it quite late when I read actually the Swift evolution proposal, but I had been using key paths for quite some time before, and I've never needed to use them. But it's nice to know that they do exist. But it's definitely feels like black magic. So back to this topic of data binding. So I want to implement data binding between a view controller and a view model, meaning that I want that when something changes in my view model, my view is updated automatically, and vice versa. And we're going to take a look at how it would look like in UIKit. So UIKit, you would have, it's a simple version of MVVM. There are different ways to do it. I'm doing just a very simple version because I want to focus more on the binding, and in order to have a binding that makes sense, that is kind of like, it feels like a real world thing, doing MVVM is a good example. So I have my class viewModel, which is an S object, and it stores a property name, which is an optional string. Okay, then we have the class viewController, which inherits from UI viewController. It stores a viewModel. It also stores a text field. And as you can see, I am setting up the text field in the UI, so just putting it into the center and then setting a placeholder, some basic style. And finally, I set a target on the text field for the event editing change. So when the value in the text field changes, I want to call the method textFieldItChange. And in textFieldItChange, I want to update the viewModel. So when the UI changes, I want to make sure that the viewModel is updated. So let's run this code, and we'll be able to see whether this works, because as you can see, I've added a property observer to print to the console whenever there is a new name set on the viewModel. So let's try and show the live view. So this is the moment where either it works or it crashes. So it seems to work. And as you can see, as I type, the binding between the view and the view model is indeed operational because every new value set to the property on the view model is indeed printed to the console. So it works. However, the syntax is not great because in order to make it work, we had to introduce this text field did change method, which is at Objective-C. We had to refer to it through an hashtag selector. It's a lot of legacy stuff that we can still use in Swift, but that we would like to avoid as much as possible. And so it would be pretty cool if we had a way to implement a binding where we would say, okay, the editing change, where we could say that the text in the text field is binded to the property name on the view model. And when you say it like that you want to bind a property on an object to a property on another object, I'm going to restate it. So when you say that you want to bind a property on a first object to a property on a second object, then the idea of using a key path kind of comes naturally to mind. So let's try and implement this, and then just after we'll go back to the topic of key paths on optionals. So for this, I've already implemented it actually because it's quite a lot of boilerplate code, and it's more interesting to understand how it works than to necessarily like build it yourself. So I'm defining a class binding. So this class binding will have a destination, which will be any object. And by any object, it means that it has to be an instance. It's because your view model, you expect it to be an instance. And what I'm doing in this binding is that, so is the NS object mandatory? I think it's going to become mandatory when we want to start writing to it. We will try, but I think the reason why I made it is because otherwise it doesn't work. We'll try to remove it. So the binding I would like to create, it will have a source, which will be a UI text field, a destination, which will be any object, and then a property, which will be a writable key path on the destination of type string optional. In that case, it's been hard-coded for a text field. If you wanted to do it more generic, you could, but for this example, hard-coding text field makes it a little bit easier to write and to understand, and the general ID stays the same. Here, actually, maybe I should have done it actually a reference writable key path. I might have made a small mistake. We'll see. Or maybe there was a reason for it, and I just created an issue that I will need to deal later. But let's just implement this class binding. So this class binding, first, what I need to implement is going to be an init. So let's implement the init. So the init is going to take 3 arguments. Actually, it's going to be close to a member-wise initializer. So the init will take a source, it will take a destination, and it will take a property to write to on the destination. Let me format it like this so that it's easier to read. And so first thing we're gonna do in the init is to do the member-wise initialization part. So self.source equals source, self.destination equal not description but rather destination, and self.property equal property. Then we call super.init, and we will still need to do something. We'll still need to hook the text field with the destination. But in order to hook the text field with the destination, you see at target, we need to have the Objective-C method. So we're going to implement the Objective-C method, this time inside the binding. So at least it will be encapsulated in the binding and not be part of our view controller. So I have my Objective-C method text field did change, like that. I will implement it just after. For now, I will simply do add target. So target will be self, and that's the reason why I made it NS object, because the target has to be NS object, because this is all code that comes from the good old days of Objective-C. I need to get the selector for the method text field did change, and the event is still editing changed. Okay, hopefully this code should build. Just here, it's not happy because argument of selector does not refer, maybe because I should not have put the parenthesis, I'm not sure. It seems it was that. And so what do we do in text field change? We update the property on the destination according to the source. So we're gonna do destination key path property equal source, which is the text field, dot text. And as you can see, it's the first time we use a key path to write to it. And I told you in the beginning that that the key path was key paths were equivalent to both getters and setters. At least writable key paths were also equivalent to setters. Here we have an example of it, and I just need to unwrap my destination so that if there is nil, I just do nothing. So let's see. Does this work? It should work normally. I'm gonna try to build the code all the way up to line 32. Seems to build without error. So we are almost there. Then we need to implement an extension on binding so that from a binding, we are able to bind the text of the text field. Sorry, I made a mistake at the beginning. I implement an extension on text field with a method bind text so that I am able to bind the text of a text field to a destination on a given property. And this returns a binding. So I'm just going to follow the type as we've done lots of time in this course. So I create a binding. So the source is self because I'm in extension of UI text field. And for the destination and the property, they've just been passed to me as an argument. So actually, I just typed garbage, not description, destination, and property. So we have our binding implemented. As you can see, it acts kind of like a delegate in a way, in the sense that it doesn't retain neither the text field nor the destination, but when the text field emits the event editing change, if there is a destination around, it's gonna try and update its property with the new value in the text of the text field. So we are almost there. Here I just need to make it a reference writable key path. Let's see. Does it build all the way to line 40? Seems like it does. And so, actually, I think we've done everything we needed. And so now what I can do is that in my view controller, I can have an array of bindings. And when I'm in view did load, I can say, okay, I'm creating my binding. My binding I created by saying name text field bind to view model on the property \name. And I'm storing the binding in the array because something needs to keep the binding in memory. Otherwise, it would just be deallocated. And so it wouldn't be able to listen anymore to the changes. And now, when I run the code, we should be able to see that it still works as expected, except that now, I didn't mean to do that. I clicked on the wrong button. Okay, here. So if I type, you can see that the binding is still working as expected. The view model is still being updated. And what's great is that now there is no trace left of Objective-C in my view controller. Everything that is Objective-C oriented, like the @Objective-C method, for instance, or the hashtag selector, is encapsulated inside the binding. And my view controller only cares about implementing a binding. So once again, it's not necessarily something that I would argue that you implement in your UIKit projects, because in order to make it work correctly, I'm sure that there are tons of edge cases that we haven't covered. However, what I wanted to show you is how this kind of syntax is implemented under the hood. Because if you know Combine, maybe if you've seen the live streams I've done on Combine in the weeks before, you might know that there is in Combine a method called assign to on that allows you to assign the values emitted by a publisher to an instance on a given property. And so this example, my goal with it is to give you a sense, to give you an idea of how such syntax can be implemented under the hood. And once again, I'm sure that in your apps, maybe you have problems that can be solved by such a syntax. And so now you know the basics of how you implement such a syntax. And as often in software engineering, knowing that something is possible is like 50% of the job, because when you know something is possible, then you know that you can search for it, you know that you can ask help to implement it, and basically the other part of making it work is within your reach. Whereas if you don't know that something exists, well, you just don't know, and you don't even have the idea to explore the possibility. So that was my goal with this training course, to show you how key paths work, to show you lots of examples of how key paths can be used. In the last page, I've put you some links to go further, and then we will take care of talking about optional key paths, because I haven't forgotten about that one. It seems a very interesting topic. So the two first links are the evolution proposals about integrating first key paths. So this link is a document that was written to motivate why key paths should be added to Swift. Very interesting. It talks about very interesting edge cases, like what was mentioned, the fact you can take a key path to an element in an array or a dictionary. This second proposal is about the code that turns key paths into functions, which I've showed you at the beginning. It also explains why they implemented it, the alternatives they've considered, the potential issue it could raise that they have to take into account. So it's very interesting. It gives you this kind of nice like backstage look into how Swift has evolved. And then a few other links. So an article from John Sandel on the powers of key paths in Swift. It's from a few years ago, but key paths haven't changed since they were introduced that much. So I would say the content is still very much usable. And a link to a talk from 2019 at TrySwift Tokyo, which I had particularly enjoyed. And so in the years 2018, 2019, there were lots of talks around key paths, because there were these nice new features of Swift. And what's very interesting is that key paths, they were introduced, I think, end of 2017 or early 2018. And they became really central to Swift when SwiftUI came out in 2019 and started to make a lot of use with key paths and also combine. But during this gap, there was this gap of 1 year where key paths were in Swift, but almost all of the APIs from Apple were not using them. There was a wrapper around key value observing that used key path, but I think it was the only API that used them. So there was this thing of like, why are they for? People like me made conference talks to talk about them, and then SwiftUI and Combine were released, and it all made sense why key path had been introduced, because they just make... imagine if every time when you need to use a key path in SwiftUI, you had to use a closure, your code would be full of curly braces and potential bugs, and it wouldn't be a nice experience. And finally, the link to the library I mentioned, so the link that the library that allows you to do like SQL-like data manipulation. So it's the overloads for the operators we've implemented. You can find this library. I tried to implement as many overloads as possible, so you can have a look. It can be interesting to learn. Today, with the predicate system like being built in Swift and being released very soon, I wouldn't necessarily argue that you should use it, but at least to understand like how you can build something with key path, I think it can be an interesting to have a look at it. And so to finish, let's have a look at these optional key paths you were mentioning. So actually, I am not 100% sure what you were mentioning, so I'm going to do a quick Google search of key path optional just to see. Key path on optional value. Oh, okay. I think I see what you mean. So let's say that I have a struct, which I will call a person, and that person can have a name, but might also not have a name. So name is optional string. So then I can take a key path to the name, but if I want to take a key path to the count, I need to put a question mark because the name might not be there. I think this might be what you were referring to. And same way, I could also do a force and wrap. So you have these two syntaxes, which once again makes sense because a key path, it's a literal syntax to refer to how to invoke a property. And since in Swift, when you interact with an optional property, you have to decide whether you want to use optional chaining or force and wrapping, then it makes sense that you also have to make the same decision when using a key path. So thanks for mentioning it because I had forgotten to show it in the examples. But at least since when you try to use a key path, when you try to compose a key path with an optional property, Xcode and Swift add the question mark by themselves, it becomes like pretty much self-explanatory. But thank you for mentioning it because it was great that I could also mention it at the end of the course. Okay, well, it's been a little bit more than 2 hours. I expect it to be around like 2 hours, something like that. I hope you've enjoyed this course. It was kind of nice to go back to key paths and to go back to this very very language level feature compared to what I had done before, training course on Swift UI and one on Combine, which are more like frameworks. Here it's very it's very basic because it's something very low level, and so you need to do a lot more setup in order to show context in which it can be used. But that was super interesting. I hope you've enjoyed it. Once again, I want to say a big thank you to people in the chat that asked great questions, made great remarks, because every time I do a training course, I always realize that there is something that I had forgotten to mention and someone mentions it in the chat, and so I can explain it, and it adds this thing that would have otherwise been missing. So it's always great to have this experience. And since we're at the end, I can tell you that this is only the first of a 2-part training course. So this course is called How to Master Modern Swift Syntaxes. If I remember it, there is a plural on syntaxes. So we saw key path, which is this first modern Swift syntax that has become ubiquitous in most modern Swift frameworks. But there is also another such syntax, which is property wrappers. And so we will see how to use property wrappers in the next live stream. So either next week or in 3 weeks. I'm not sure. It will depend on my availability. But this is coming, and so it will be the same format with a playground. We will cover property wrappers and all the cool things that you can do with them. And I think it's the moment where I have to stop talking. Say once again, thank you for watching, and see you next time. Enjoy your evening, your rest of your day, depending on where you are in the world. Bye bye.